Hi, we are the Fixed-Wing UAV Silver Team. Our objective for this project is to build a UAV that has a pusher motor and carry a detachable liquid payload ranging from 25 to 35 fluid ounces. Our team decided to design a twin-boom UAV that will allow clearance for a pusher motor and fuselage space to hold our payload and avionics.
In the design process, the team had three major iterations. Within each iteration, there were multiple designs to get to the final product. After having an idea of the materials, dimensions, and weight of the UAV, the team decided to run an ECalc simulation to get an estimated thrust value generated by the motor. By inputting the correct models for both the motor, propeller, and battery, we can see that the estimated thrust produced by the motor is around 4.8 kilograms. From there, we're able to input those values into Fusion 360 and run an FEA analysis. And as we can see, the factor of safety is above 6, right where the motor will be mounted into the fuselage. Furthermore, we ran FEA analysis on both the wings and the twin boom from values obtained by doing CFD analysis. As we can see, the factor of safety is above 6 on most of the surface area of the wing, and the displacement is very minimal of being 0.241 millimeters on the twin boom.
XFLR5 was used to analyze the wing and compare different airfoils. The Clark White airfoil was chosen due to its flight characteristics and its ease of construction. Based on a predicted level flight velocity of 13 meters per second, a couple of examples of the capabilities of XFLR5 are determining the expected angle of attack at level flight, as well as the predicted stall speed by using the coefficient of lift versus angle of attack graph. Predictions on lift, induced drag, viscous drag, and downwash produced on the wing were also analyzed. ANSYS Fluent aided in analysis of airflow over the wing in a wind tunnel setup. The pressure distribution over the wing is just one of several elements that can be analyzed in order to simulate lift generation.
Here we have our avionics setup. Through researching motors that meet the needs of our UAV, we selected the motor shown on the slide. We then selected a 6S LiPo battery and a 100 amp electronic speed controller. We used 5 9G microservos to adjust the control surfaces, one for each aileron, one for each rudder, and one for the elevator. The ESC, along with the 5 servos, were all connected to the receiver to allow for wireless control through the transmitter.
Multiple procedures were carried out during the testing phase in order to verify and validate such values or functions for critical components that would be integrated into the UAV. Before carrying out physical tests, software such as ECalc was helpful in predicting the potential thrust values from the selected propellers. 2 separate analyses were run through the software in order to see how the thrust, speed, and efficiency would vary with both propellers. Additionally, the provided spec sheet for the Scorpion S2 motor was referenced to cross-check the thrust values obtained through the ECalc analyses. In order to run a thrust test, a thrust stand was essential. Once the thrust stand was assembled, the Scorpion S2 motor, 13x8 propeller, 100 rated amp ESC, receiver, and LiPo battery were integrated onto the system. The thrust test produced roughly 7.5 pounds of force from the 13x8 propeller and 7 pounds of force from the 13x6.5 propeller. A quick center of gravity test was conducted on the fuselage. This was done so the team could see how the CG would vary in regard to the varying ounces of water that the UAV would have to transport during flight. Critical components such as the servos, ESC, and battery were also tested to ensure there wasn't any issues with their associated functions. The team also did a range test to see if the receiver would be able to pick up signals from the transmitter once it was integrated into the fuselage of the UAV.
Hello, I'm going to talk about the build and manufacturing of this UAV. As you can see on this picture, most of the UAV is carbon fiber. We decided to go with carbon fiber for many reasons. The first one is that it's light and strong, and also because we had the opportunity to make the carbon fiber ourselves, since I was able to provide some carbon fiber from my work. So the first step is to make the carbon fiber panels for the fuselage as well as the boom. This is a picture of the team making the panels. This is a picture of some panel made with the balsa template that we had for the trimming. This is the trimming of the plates. This is the plates assembled in the beginning of the fuselage, and we can see how light it is. We also decided to get the wings and the nose foam cut. We decided to get it cut at UCF in the lab, but it was not strong enough, so we decided to also reinforce it with carbon fiber on both sides. This is a picture of the process of the laying of the carbon fiber. This is the finishing product of the wings and the nose. On the right side, as here you can see, this is our fuselage with all the panels, as well as the Velcro on the top, because we needed a way to open the fuselage fast and easy, so we decided to go with Velcro to remove the top panel. This is the boom, which is carbon fiber rods connected to 3D printed connectors, as well as carbon fiber deck and carbon fiber elevator and vertical stabilizers. This is the fuselage with all the avionics and the containers test fitted into them. And this is the wings on the left side are almost done, and the landing gear we're going to go with, which is a carbon fiber back frame as well as a front suspension setup landing gear. And this is a dry fit of all the parts and components after it was all manufactured.
Current status. As mentioned before by Ilan, all the parts for the fully functioning UAV are in hand and ready for full assembly. The UAV will be assembled and ready for first full-scale test flight in the final week of November. Following the test flight will be the final flight day, in which the UAV will complete 3 flight circuits, with each flight having a varying payload, one with 25 fluid ounces, one with 32 fluid ounces, and one with 35 fluid ounces respectively. The team is also in contact with pilots from Moonport modelers to ensure there is good piloting for the UAV on the final flight day. Some challenges faced throughout the project included supply chain issues for certain parts. This was circumvented by finding equivalent replacement parts and use of a different supplier. Another challenge was that of weather and school closure. Due to the 2 hurricanes experienced this semester, there was some unforeseen delay in the project's progress. This issue, however, was managed through great team coordination and hard work to ensure the project remained on schedule. Overall, there are many difficulties facing this project that have been overcome, allowing for the project to reach completion. Thank you for listening to Team Silver's Senior Design Showcase video.